OpenCV keeps getting better year by year, and there's a lot of people who seem to be contributing to not only the library but also to the documentation. So I'm looking at one of the latest versions of the OpenCV. I think OpenCV 24 or whichever version this is, the latest documentation that I could get hold of on the site, and long back, it was difficult to get such good Python code examples. There used to be a lot of C++ code examples, and slightly difficult for somebody like me who does not know C++. So okay, so what I'm trying to do over here is again slightly experimental. And even though it says TensorFlow GPU environment, and that is what I have activated, this is not really much of TensorFlow over here right now, mostly OpenCV. So first, just the imports CV2, and okay, so within this there is surf, which we will not get to do. Surf we will not be able to, because it says it has no attribute surf create, because this is a patented algorithm, and for this you need to do a CMake and things to that effect. I have tried that earlier, and I don't know if I should do this right now on a video, but let me see. So long back, the CV 2020, this had to do, you know, with a lot of yeah. So here and maybe one more, yeah. Yeah, so this all the CMake and all that happened 2 years back, because of SIFT not so ended up uh, doing couple of CMakes for OpenCV, and finally I think I got it working, but I don't know, something again. I'm not sure. Maybe it still works on my system. Maybe I've broken it after that because of some CUDA and other things that I've been doing with my GPU for TensorFlow and all that. So maybe I don't know. I won't get into this right now. But yes, if you really want all of those features, and if you want surf to work, you should try that out. CMake is your friend over there. Okay, I'll not confuse the agenda for this. So what I'm doing is, quickly I'm just looking at some brute force matching of SIFT features, and this code is taken from here. This code is all from here, and few other references I found on the net. Nothing very special. Code is very simple. So basically just reading the image. So in this input directory, from there I am reading my image. Let me go to the input directory. Oh, sorry, I need to pause this. Okay, so this is the input directory, and within the input directory, what I basically did was, I think I got this from that Caltech datasets. I got a lot of images of aeroplanes and guitars, and I put them over here. I got this from the Caltech dataset. And why did I get the Caltech dataset? Because I think I was following some code from some book, and that's the reason I downloaded that. So what we are looking at over here is, so it says image 12. So this is the image. So this is the input image. Uh, it's of a aircraft, and what we are trying to do is, we will plot some uh, SIFT features on this. And why we will want to do that? Because there is different kinds of feature detection that you can do over here, and the number of features also differs. So over here it's 150, then this 350, then this is 50. So I call it the small orb small. I just call this the orb, and I call this a SIFT. The surf, obviously we don't have this, so surf I'm not doing right now. Um, so so this is one image that we'll be reading in. Then there are two other images, which is from within that directory. I have a planes subdirectory, and within which I have these two images. So let's have a look at that also. So planes and 48 and 49, 48 and 49. Why 48 and 49? Because these are two if not the same aircraft, but almost the same aircraft, I presume, or maybe the same one. So one is down on the ground, the other one's up in the air. Yeah, it's the same aircraft, right? So that's the reason I've chosen these two images, 48 and 49. And so once I've read in these images, so this one I'm reading in here, and this one I'm reading in here. So image underscore 0 and image underscore 1. Once we've read these, we want to do a brute force match on this. So this we come to later. So for first, just getting these features out, and so this is very simple. OpenCV 2 code, SIFT create, orb create, orb create, orb create. The only difference over here is that the number of features is less. There we have 350, here it's 50. Okay, so what we will get is key points SIFT and key points orb, and we'll get descriptors. So descriptors for these key points, and again, so like what we've done here, we've taken that SIFT create object and all that we are calling the detect and compute. And image is there and none, I don't remember what exactly is the but you can check it over here in this document. You'll be able to check that. So why we are passing the none parameter over there, what else are the options, what can be going in there. And so orb okay for two different images, and then orb small only for one particular image, which is the first image, the biplane, or not the biplane, the normal plane. So maybe I don't know which one they call the biplane. Probably the one with the, okay. Any which ways. So we'll just get to see this. And once this image comes up, so the first image, so just to show you that this is the first one, and this is the second one, and this is the third one. So once we bring up these images, they'll come up in this manner. And just to go from the first image to the second image and the third image, when they're getting displayed, you just have to wait key means any key that is pressed, it will destroy all windows at that particular time. So obviously there'll be just one window which will be that image which we'll be showing, so it will destroy that image, which is okay with us. And then we are trying to write that image as orb rich key points. And I put this 18 underscore 3 just to show that this is 18th March and this is when I'm recording this video, and this is when this image is getting written, because there are earlier images. I didn't really want to clean up that directory, so yeah, so here it is. Okay, so the output directory, so this is the input directory, the output directory will come up here. I just did one of these images right now about a while back, so it gave me this, right? So this is the rich key points. Yeah, so this is how simple this code is, and I'm just logging it into a log file in case it throws an error or there is something which uh, happens that I probably want to show you. There's nothing right now as of now, just probably one of these image names or something is getting logged somewhere, which is okay. So yeah, so that's about it. And this is the first image. So what exactly are rich key points versus non-rich key points? So if you'll note, what is happening here is that whenever a key point is picked up, there is a, maybe I don't know if you can see this, but there is a circle which is formed around that key point, and there is a certain perpendicular that is falling onto that circle, so to say, perpendicular, or falling onto that circle. So there is certain theory behind this, and why we want to do rich key points versus just key points, and these are just key points, right? And this is the second image. So once you've seen the image, I'll try and go through the code again so that we can understand what is happening here. And this is the third. Here you see very less number of key points, and these are not the rich key points. And in case anybody is wondering what is happening when I'm moving my mouse, that's basically the RGB values of that particular point where my mouse is on the image. Those are getting displayed, and then X and Y coordinates are getting displayed. So if I keep going up uh, towards the left of the image, then my x and y coordinates reduce. If I come to the bottom right of the image, they increase the most, the x being the most. And if I go in this manner left, so then again my x is reducing, my y is still pretty much at 148 or whatever, at around 150, because I think 150 153 is my max y. So my y is basically the height of this image, and the x is the width. If I'm going extreme left, my x is reducing and my y is still the same. If I'm going up, you'll see my y is reducing, y has come to 0. My x is still showing as 13. Yeah, somewhere here, I think, yeah, x is again minimum. Over here on the right side, my so this is how basically the coordinates work. And the RGB, so if you note right now over here, the RGB is sticking around to somewhere around, the red is 200 204 something like that, because I'm roaming around this gray area. So is my G, so is my B, so all of them are kind of, somewhere about, let's say in the proximity of 200. If I were to go in a very very dark area, so everything got reduced because it's a dark area. If I go into a white area, again they've gone beyond 200, so that is, all three channels, uh, when the color is white, all three channels are basically max. If I was on a image part which is pure white, very shiny bright, then all of them would be, if I remember correctly, 255 each. uh, yeah, so that is how it is. And let me go here. So yeah, so I think I've hit the point where the red is very high, the blue is high, and the green is very low. So one of these, let's see, maybe we'll get to a point. Yeah, over here the green is quite high. So maybe we are on that green part of it. Here the green is extremely high. Yeah. So this is how it basically works. Again, I think I'm on something which is, the green could be much higher. Yeah. So any which ways. So now hitting it. So now we come to the brute force match. So those two different images of the same aircraft, it seems, uh, these results are not very good. So if you say, yeah, the results are good, the results are obviously not good. So the matching is not happening very properly. But I'm glad to see that at least some of them are giving us a bit of an idea that how this thing works. Uh, and I have not really tried much. This is just a very very basic implementation of this. And okay, so okay, I've gone through most of the code on this, and this is again, from the document itself. So it says the orb is, that it came from the OpenCV labs. So the orb part of it is something which will, uh, you know um the orb will be free, so to say, as an algorithm to use for anybody who's using OpenCV now or maybe in the future also. Whereas SIFT and SURF are both patented. So SIFT, I think, to some extent, we are getting to use it still, but SURF won't happen unless, of course, you try that CMake part of it, or there were some other options. But I really couldn't make it work. I tried a lot of things over here. Okay. Let's see if I, yeah, so OpenCV contrib, there is some different versions that people talk about, that you get this installed and that one installed. But ultimately I think I had to work with this 3.4 and some other. Yeah, so so all of this is up in the Git, so in case anybody wants to have a look and have a look at this, this is my Git repo for this. So again, so now let's run this on the guitars, because we just did this. We just did it on the image. This we've just done, and output there bf. I think this is the one. Yeah, this is from earlier. This is from 2nd of March, and what we have right now, I think, is this. Yeah. So the same image, but run at two different times. That's all. Okay. Now, I also want to run it on the guitar images. The guitar images, give certain better results, or at least I thought so. So let me try it on the guitar images, and so this is not my input image. I need to find. Yeah, so we picked up two of these guitar images, and this seems to be much better. But I really can't be sure, but at least for a guitar, wherever this thing is picking up these points, it is always on the fretboard. At least I can see only a fretboard uh, being matched with the other image's fretboard. In certain cases, of course, there is some there is some sound equipment lying over there, maybe a speaker or a woofer or whatever that is, and it's gone and picked up one of those round knobs on that in place of some position on the fretboard. But this still seems to be okay. And again, like I said, it's just a brute force match. There's nothing that we have done. Uh, I have not changed it. It's just I'm just pulling in the code and that's all. Uh, yeah, but on the guitar images, this still seems to be slightly much better. And I ran this a couple of times that day. And within the input there, okay, these images are still there. So sorry, output there. So I can show these to you. Uh, this is what it looked like. Yeah, so like I said, fretboard to fretboard. Most of them are fretboard to fretboard. Of course, over here, there's one that's gone totally, and these are not, the plotting of the lines is not very clear. But if you try this code out yourself, very simple code. We can see the matches are somewhere the matches are okay. Like a couple of these green yellow lines which are going from the nose tip to the nose tip, and these are not the same aircraft. They're not even in the they're definitely not the same aircraft. At least the nose tips it is matching. Rest we will obviously have to, and it is also matching this part, which is a big fluke. I would say. How would it even make out that this part of it is same as this part? I don't know. I am not very sure. But at least, and the tires, at least I think it got one or two matches over here, if not more than one or two. Yeah, so there is something to it, but I obviously have not gone into the detail of this to understand how this is happening. So we need to spend some time to understand, and even if it is good enough or not. And this is just playing around with those rich and non-rich. Yeah. So all of this code is there. Anybody who wants to try can try this out. And that's about it for the OpenCV one. Besides that, I haven't done much here. Uh, yeah. So this is just a basic prep of trying to match images and trying to match objects. Then I'm getting into few things with PyTorch, and yeah. So OpenCV is just to understand the basics and then to go ahead.